Hello everybody, welcome to Hardware Horizon. So let us kickstart the study series with the very basics. And what is more basic to electronic devices than the materials that make them, right? Yes, we are talking about semiconductors. Semiconductors form the very heart of modern electronics. So it is very important for us to understand what they actually are and how do they exactly work. So let us do that. Even before the introduction of semiconductors and their uses, vacuum tubes were the only available devices for applications such as switching, signal amplification, and such. Even though they were highly functional, there were several shortcomings related to the vacuum tubes. First of all, they were very bulky, and obviously, the cost of maintenance of such huge devices was also very high. Then they required very high operating voltages. So all in all, they were not very efficient. So when semiconductor devices such as transistors were introduced, they quickly replaced the vacuum tubes and became a force in electronics world. What exactly are the semiconductors? Well, as the name itself suggests, semiconductors are material whose electrical conductivity lies that of between conductors and insulators. What is electrical conductivity now? Well, it is a measure of how well a material can allow electric current to flow through it. And if you remember from your high school days, conductors are materials that allows electricity to pass through them easily, while insulators block them. Semiconductors lie somewhere in the middle now. Usually, elements of group 14 of the periodic table make very good semiconductors. For example, silicon. In fact, silicon is one of the most commonly used semiconductor material, followed by a compound known as gallium arsenide. Pure silicon in room temperature has very low conductivity. Why? For that, let us go back to the crystal lattice structure of a silicon. For the sake of simplicity, we will only be focusing on this green silicon atom. Now, as already discussed, silicon belongs to group 14 of the periodic table, which means, like its members, silicon also has 4 electrons in its outermost or valence shell. This valence electrons for the green silicon atom is shown in the color blue. Now, each of these 4 blue electrons can form a bond with an electron from a neighboring silicon atom. So to this green silicon atom, there are 4 neighboring silicon atoms which are in yellow. So there will be 4 bonds being made. These bonds are very strong in nature and are called covalent bonds. Hence, for each silicon atom, we will have 4 covalent bonds. This strong bonding structure keeps the electrons very tightly bound, which means that at room temperature, there are very few free electrons left to conduct electricity. This is the reason for the low conductivity of pure silicon in room temperature. Now suppose instead of pure silicon, we introduce some foreign atoms into the system, say from the adjacent rows of the periodic table. This method of introducing atoms from group 5 or group 3 of the periodic table into pure semiconductor material is called doping. How doping affects conductivity? Let us see. Now let us go back to the same silicon example. If we replace some of the silicon atoms, say with a pentavalent atom, that is, atoms that have 5 electrons in its valence shell, like phosphorus, arsenic, or antimony, what happens in this case? Well, out of the 5 valence electrons, 4 electrons will again form strong covalent bonds with 4 neighboring silicon atoms. But 1 electron will still be left out, and this electron can freely move in the system, and this increases electrical conductivity. This is called N-type doping, and the material thus formed N-type semiconductor. Now, instead of a pentavalent atom, let's say we introduce trivalent atoms in the system. These are nothing but atoms that have 3 electrons in its valence shell, like boron, indium, or gallium. All the 3 available electrons now will form covalent bonds with 3 neighboring silicon atoms. But from the usual case, 1 silicon atom will be left with no electron to bond with. This vacant electron position is called a hole. In nature, everything tries to be stable, right? Yes. So as soon as a hole is formed, a neighboring electron will try to come and fill its place, which means it can also be viewed as the hole moving from its original position to the position from which the electron has left. Again, another neighboring electron will come and fill this hole's place. Thus, a hole can be visualized as an independent charge carrier which is moving freely in the system but in a direction opposite to that of electrons. This is called p-type doping, and the material thus formed p-type semiconductor. Thus, in semiconductors, we have 2 types of charge carriers, electrons and holes. Now let us try to understand the same thing in terms of energy bands. Energy bands are nothing but some energy states or ranges that electrons of an atom can possess. Now, in a pure silicon in room temperature, all its valence or outermost electrons reside in a band called valence band. While in this band, the electrons are still adhered to the atom and they are not free to move. But by increasing temperature or by, say, photon absorption, some of these electrons get enough energy to cross the potential barrier or energy gap or the region where no electrons can exist and move to a higher energy level, which is called the conduction band. In the conduction band, the electrons become free to move and they become what is called as conduction electrons, and naturally the conductivity increases. This ability of semiconductors, in which we can control its electrical conductivity by external processes such as doping or thermal excitation, is what makes them so popular in modern electronics. Unlike metals, where the conductivity is almost fixed, one way of classifying semiconductors is based on its purity. Intrinsic semiconductors are ones with no impurities. After doping, we get extrinsic semiconductors. And based on the type of impurities introduced, we have either p-type extrinsic semiconductor or n-type extrinsic semiconductor. Now, separately, this p and n-type semiconductors are pretty much useless. But when we combine them, a special region gets formed in their intersection, and this is called the p-n junction. The p-n junction and its functionality forms the basis of most of the semiconductor devices like diodes, transistors, and thyristors. We'll be covering p-n junction in the next video. So let's do a quick recap of whatever we learned today. So we learned what are semiconductors and what is the basic structure of semiconductor materials. We learned what is doping and how doping increases electrical conductivity in semiconductor materials like silicon. We understood the classification of semiconductors based on its purity. And finally, we saw what is p-n junction and how it forms the basis of semiconductor devices. So that is all. You'll find the notes and worksheets in the description box. Please try to solve them to get a clear idea of this topic. If you have any questions, please leave it in the comments below. And if you like this video, do not forget to subscribe to this channel. I'll see you in the next video. Ta-da!